Hello, everyone. Thank you for coming to this demo lesson. And I'll talk about what my planned math courses are going to be after some of you filled out the questionnaires. Okay, and then I will proceed to present the math point geometry method. Okay. And if we have time, I'll try to answer some questions from you. Okay. And before I start, let me first point out that at the lower right corner of your video screen, there is a rectangle. Okay. And you can click it to toggle from horizontal to vertical, which corresponds to full screen and partial screen. So during my presentation, you may want to toggle to the full screen mode. Okay. And I think with that, we can start. Let me first change to full screen. Okay. So the main purpose for this trial lesson is actually to get those people who haven't used the DDAR learning app familiar with the system, particularly comfortable with the platform, which is what I'm going to use for all the four classes I'm opening. Okay, so I want to highlight again the platform I'm going to use. Okay, so it's a an app that and some of my team members developed, and it's specifically for online education. Okay, that's why I'm using it. So another thing I want to point out is that the format for all the four courses will be live video with interactions. Today, because of time constraint, we may not have as many as I would like, but in the real lessons, just keep in mind that there will be plenty of interactions between me and the students. Okay. And so first, let me talk about the introduction level competition math, which is introduction to algebra and the introduction to geometry. The prerequisite for both is just the completion of pre-algebra. Okay. And the textbooks I'm going to use is the AOPS Introduction to Algebra and the Introduction to Geometry, respectively. I will strive to cover at least 85% of the examples and the exercises from the books through either lectures or assignments. But my main focus will be on teaching how to think, okay, which is reflected in my teaching motto, okay, not just know the answers, but also learn how to think. Okay, I like to think that's what differentiates my teaching from some other teaching that your children may have gotten used to. Okay, and for these two classes, they are both 25 weeks for a total of 50 hours, with 2 hours per week. And you can see they both start on at the beginning of June and runs until the third week of November. Okay, it's a half year. It's 25 weeks. Okay, and for algebra, it's the lesson is from 3:30 to 5:30 PST p.m. on Saturdays, and for geometry, it's the same time but on Sundays. Okay, and the price is $800 each. Okay, So the price was arrived at after taking into account the inputs that some of you provided in the questionnaire. So thank you very much for that. Okay, so that's the introductory courses. And then I will also open two summer camps, the AMC 1012 summer camp and the AMY summer camp. Again, I will be using the same platform. Some of you are already very familiar with it after taking my February AMY geometry class. Okay, so I hope these some of the new members joining today will feel comfortable using it, just like all these 50 other students who did in February. Okay, so the prerequisite for both is just basic knowledge or basic training in 4 of the contest mathematical subjects in mathematics, okay, which is algebra, geometry, combinatorics, and number theory, AGCN in short, okay. And but there is also a recommended prerequisite, even though it's not required, but it's highly recommended in order for you to get the most out of these camps. So for the AMC 1012 camp, your AMC 10 should be at least 90, or AMC 12 at least 80. Okay, and for the AMY camp, your AMY score from past examinations should be at least 5. Okay, because for both, I will be concentrating on the last 10 problems, okay, of the real contests. So for MC 1012, there are a total of 25 questions. So the last 10 would be from problem 16 to problem 25. Okay, and because the AMY has 15 problems in the test, so the last 10 would be from problem 6 to problem 15. So when you decide on which camps you want to sign up or whether you want to sign up, so keep that in mind, okay? Otherwise, you may not get out, as much as you would like. So please be forewarned, okay? And the content for both classes will be reviewing most the concepts tested in the respective tests. So, but again, the focus will be on teaching a unique, systematic, repeatable, and proven problem-solving methodology. Okay. So, for both camps, it takes 2 weeks, but the lessons are only on weekdays, Monday through Fridays, and for each day there will be a 3-hour continuous lesson. Okay, so for a total of for 10 days, for a total of 30 hours per session. Each camp has 2 sessions. Like for the AMC, there's a session that starts on Monday, June the 14th, and there's another session that repeats it, okay, on July, that starts on July the 26th, okay, and you can see the times here, and but all of these will be in a course that's to be set up right after this trial lesson, okay, but the reason why I delayed until after this is done is because I don't want people to sign up to pay for it before they are sure what the platform is like, or whether they would agree with my teaching philosophy. So that's the main purpose of this trial lesson, is to get everyone familiar with the platform as well as the methodology, so you feel comfortable before signing up, okay? And for AMY, the same thing. So there are two sessions, identical sessions. One that starts on July 5th, the other on August 9th. So for each session, it also costs $800. Okay. Even though, according to the questionnaires, the prices actually could be meaningfully higher than this, but I just wanted to be more quote quote inclusive, as well as more auspicious in choosing the number. So I chose the number $800. Okay. So again, thank you for those people who provided their valuable inputs in the questionnaires. Okay. So with that, all this information will be in the respective course catalogs in DDAR Learning. So you don't have to remember everything or anything. So this is just a quick review because I haven't notified anybody about the times as well as the prices. So I just want you guys to have the first knowledge of it. So with that, let me dive right into the main subject of this trial lesson, which is mass point geometry. Okay. And it's a very, very powerful and robust method for computing these 9-segment length or ratios in polygons, particularly most commonly in triangles. Okay. And it's based on the concept of center of mass in physics. It was invented by the guy called Franz Mobius in 1827, but it was popularized by New York high school students of all the people in the 1960s. I guess they, just like some of you guys, were just befuddled by the geometry taught in school, I guess. So they basically revitalized this nice trick from the 19th century, okay? And this method actually was generalized to an even more powerful method. It's called barycentric coordinates, which I may cover in my Amy camp if time permits, okay? And at the core of the method is to systematically assign weights or masses to points so that the length are proportional, inversely proportional to the weights at the end points of a 9-segment. And the steps usually that takes to solve a problem is first you choose a point or center of mass in the figure to balance the entire figure around, okay? And then you can start with an arbitrary point to assign the first weight. Usually that number is it's up to you, but usually it's chosen so that the computations down the road are easier, okay? And after that, all other weights are derived from the balancing rule I call, okay? So basically, let's say you have two masses, MA, MB, and then between them there is a lever point, okay, let's say it's C. And to balance the two masses, MA and MB, around the C, using C as the lever or the fulcrum, you need to have, let me denote this line segment as LA, and this one as LB. So to balance the two masses around C, you need MA times LA is equal to MB times LB. Okay, so that's the core of the method. In other words, if you know a little bit of physics, if this is satisfied, then the center of mass of A and B is what? Can somebody please quickly tell me? If this is satisfied, the center of mass of A and B is just what? Yes. Let me see. It's very nice. Okay. So, and then because C is the center of mass, so the mass for C would be the sum of the two. In other words, the two masses A and B can be replaced by a single particle mass C that amounts to Ma plus Mb. Okay. Very nice. Thank you for being interactive. Okay. Let me see whether I have some familiar faces. N123, right? You are from my February Amy geometry lesson. Welcome back. Okay. So, and then after that, it's just the propagation of this, because the new mass can be used in its respective balancing rule to find the ratios of 9 segments instead. Okay, so I think for this method, the best way to learn it is just by examples. Okay, and I divided into 3 common patterns that pretty much is every possible way that you could encounter in using mass point geometry. Okay, so the first one is called concurrent seviance. Let me draw the diagram first. So there is a triangle ABC. And then this is CE is 3 times AE. And then CBF is 3 times AF. And then BE and CF intersects at O. And then you connect AO, extends it to intersect with BC at D. Now you're asked to calculate OB over OE and OD over OA. Okay. So this is a very, very straightforward, typical case of mass point geometry application. But I want to start with the most basic ones, particularly for those people who haven't learned the method. Okay. So because we know these ratios AE and CE, I like to choose remember, the first thing we want to do is to choose a point you want to balance the entire figure around. What would be an obvious choice here? Can someone please? What would be an obvious choice for really the center of mass of the system here? Or the point that you want to balance the entire figure around? Yes, it's obvious. It's because there's only a single point inside the triangle. So the choice is O, right? Okay, so to do that, first I want to balance the A and C around E in order to use the ratio between AE and CE. Because AE over C is 1/3, so I'll choose, let's say, you can choose any vertices. Usually you start with a vertex, okay? So I'll choose A to assign the first weight. I want to make it 3 because I can choose anything I want. So I choose 3. And then what would be the mass for C? Can someone please tell me? The balancing rule. So I have the mass of A is equal to 3 now. By the balancing rule, MA times AE should be MC times CE. Right? Now this is 3. AE is just 1/3 of C. So it's just the MC is just 1. You're right. Thank you. So this is 1. So for the same thing, B is also 1, right? Because AF and BF, this is just 1/3 of this, right? So as a result, what's the mass of O? Can someone please tell me what's the mass of O? Oh, no. I'm sorry. Sorry. It's a bad notation. Okay. I meant the mass of D. This is not O. Let me try to erase it. What's the mass of D? Right. The mass of D is just the mass of B plus C. Now, with this mass known, D's mass known, what ratio can I get right away? Sorry about that. Okay. So what with the mass right? I use this balancing rule in reverse between A and D. Between A and D, because I know the mass of A and D, so I know immediately the ratio of OD over OA is just inverse of the mass ratios, MA over MD. So just 3 over 2. Now, can someone please tell me how to calculate the second one? I still have the second ratio to compute for, right? So how do I do this? How do I calculate the ratio OB over OE? Yes, because OB and OE, they are on the same line as B and E, right? These are collinear. So I want to find out the masses of the endpoints of B and E. B I already know is 1. So what's the mass of E? Right? So somebody was already quick enough. That's very nice. So it's just mass of A plus mass of C, right? Because it's the center of mass of A and C. So it's 4. It's the sum of it. And then OB over OE is just the ME, the inverse ratio of the masses, over MB, which is 4, right? I hope I didn't make a mistake. Okay, so this is straightforward enough. Basically, it's very, very mechanical, okay? And it's robust. And you don't need to sweat to make, parallel lines. I mean, this can be proved, figured out with the parallel lines or even areas. But with mass point geometry, there's no need, okay? No, I never got AE. AE. I only know the ratio between AE and CE. That's one third. Oh yeah, I see what you mean. You mean this, right? Because it's one over three. I didn't want to this. So AE over CE is one third. I chose because it's ratio, so I chose one for AE and three for CE. Okay, and you can choose anything you want, or I can do the ratios, right? MA over well, MC over MA is equal to AE over CE, and that's one third. Okay, so this is just a convenient way of using the ratios in a multiplicative equation. Okay, I didn't want to write fractions. No, I didn't know that the absolute length of AE is 1. You're right. Okay. All right. Let's move on to the second pattern of mass point geometry. In this case, it says there's a triangle. I don't know whether I'll draw it in proportion, but just bear with me, okay? ABC, and it says DEF on BC. So CA DEF. Great. Okay. Yeah, you're right. Exactly right. So you can just use the ratios. I didn't want to write vertically, so I just chose some convenient numbers to reflect that ratio. Okay. So it says AE equals AF. E is on AE. E is on CA. So AE equals AF. And equals CD. Okay. And these three are equal to 2. And then BD is 3. Let me just write it out. 2, 2, 2. BD is 3. And CE is also 3. And BF is 5. Okay. So if DE and CF intersect at O, you're asked to calculate this over this, OD over OE, and this over this, OC over OF. Okay. So for this one, it's called a splitting mass. The one important thing to remember, we know CF is called a Cevian, right? This is called a Cevian. But DE, it doesn't originate from a vertex. It's the segment cuts through two sides of a triangle. These are called transversal, okay? So it's a transversal. Okay. So to handle this case, you need something called splitting mass. Basically, C has there are two separate masses at C. One is for the left side, the other for the right side. And the reason being that, for instance, you want to balance A and C, you need to satisfy this ratio, right? Satisfy CE over AE, the ratio. If you want, and then you want to balance B and C around D, It needs to satisfy BD over CD. Okay, but then A and B need to balance around F. If we don't split the mass at C, we run out of degree of freedom, which means you cannot arbitrarily choose your first weight. That's the most helpful thing, right? Because your first weight, you can choose anything you want, and then everything else will be fixed. But if we don't split the mass here at C, we run out of degree of freedom, okay? Or for our freedom of assigning the first weight arbitrarily, okay? In physics, the same thing can be reasoned like this, okay? If you don't split the mass around C, then if you want to balance A and C, there's only one way of splitting the system of three masses, A, B, C. It's A and C first, you make it balance around E, and then the only other mass left is B. You have to balance B and E. Then you won't be able to figure out the ratio around O, which is what you're asked to calculate. Okay. In any case, it's for the beginners. It may be too much to think about, but I'm trying to get the background behind it, the reasons behind why we need to split mass at C. Okay. So to do that, I always like to start with the place that's more deterministic. So let me start with the vertex A. Okay, what mass is good to assign to A? What number? 15. Okay, let me follow your advice. Somebody said, okay, holy cow, too good. Okay, you guys are good. Maybe I should implement some holdout feature on on the fast guys. Okay. In any case, let me try to use Eng 123's advice. So A is 15. Okay. So from this, what do I know immediately? Oh, yeah, right. So thank you for reminding me. Yes, yeah, it's a 3 plus 2. It's a 2, 5 side length. So B is automatically 6. Okay, because you need to balance around F. And then what else do I know? C is 10. Okay, now be careful. Remember, we need to split the masses at C. So for the 10, which is it 10? Wait. Okay. Yeah. For the 10 is which side? Oh, for side A, so the left side, okay? So the left side is 10 for C. What else can we know? So E is 25, okay. What else? So the right. So how do we get the right hand mass of C? Right? So it needs to multiply 2. Okay, let me mark it like this. The right hand side mass, you need to multiply 2 is equal to 6 times 3. So it's 18 over 2 is 9. I'm trying to illustrate to the people who haven't learned the method, okay? So And then what now, please? What do I do? But don't forget. The end goal is not to calculate the mass of O, okay? Because all we're asked to do is to calculate the ratios, these two ratios, okay? Okay, so somebody said, so the MC, you add it up, is 10 plus the left and right is 19, okay? So at this point, what do we do? Yes, don't forget what you're asked to do, okay? I'm sorry, is to calculate these two ratios, okay? These are our end goals. So, right. So somebody said, let me see. So somebody used the voice. Let me see. Oh, it's okay. No problem. Okay. So the mass at F is just the mass at A plus mass at B, which is 21. At this point, can we calculate any ratio already? But don't forget your end goal. Okay, yeah, you can chase around to find the masses for all the points, but don't forget our end goal. Our end goal is not to assign the masses; it's to what, to calculate the ratios, right? So we already know the total mass at C and the total mass at F. So what ratio can we calculate here? Right. So by the balancing rule, I can calculate the ratio OC over OF is just the inverse ratio of the mass, which is just 21 over 19, right? Remember, this is balancing around O, so you need to use the combined weight, okay? Because now it's the whole system. There's a center of mass. Right. So the mass of D is just the mass, the right hand side mass of C, 9, plus the mass of B, 6, which is 15. Okay, so as a result, OD over OE is just ME, the inverse ratio of the masses, MD, is 25 over 15. That's 5 over 3. Now, I hope you guys already noticed how easy and mechanical this process is, and it's very, very robust. Okay, and without this method, I'm sure you definitely need some kind of parallel lines, but in this case, no, it's not parallel. D is not parallel to AB. Okay. Or the ratios of areas, okay? Right, yeah. So this is the very, very important case of splitting the mass. So basically, you want to split the mass at the point that, that has a CV intersecting with a transversal, okay? For any such point, you need to split the mass. Okay, let me mark it here. So C, because it has a transversal CF intersecting, it's a CV intersecting with the transversal DE. So for any such point, C, you need to split the mass. Okay, yeah. So for some of you, so if you are already very fluent in this method, when you answer questions, can you try to hold it a little bit? We haven't implemented the gate for answers, but I think some of you are right. I mean, give other people time to think. Okay, please. Okay. So this is the splitting mass pattern that you will encounter in applying the method. And then the third and last pattern is the mixed one, okay, which is the most commonly encountered scenarios, okay. So in this case, this is in triangle ABC. I'm sorry. Is it ABC? Again, I don't know whether I would draw it proportionally. And then DE are on sides BC and AB. So D is somewhere on BC and E is on CA, respectively. And with AEAF, so F is AEAF is 2. Let me do this first. E is on AC, F is on AB. And then BD is equal to DC, is equal to 2, okay? And then F and G are on side AB with G between F and B. So G should be somewhere here, okay? And then BE intersects CF at O1. This is O1. And then BE intersects DG at O2. Okay. And then so your let me mark all those lengths so we don't need to look up. AEF 2, 2, 2, CD is 2, DB is 2, and then FG is 1, BG is 3, C is 3, okay? So what's the difficulty here that we haven't covered yet with this problem? Okay, everybody, please no bickering. We are here to learn, okay? Thank you. So can someone please tell me what's the difficulty with this problem? We're asked to calculate this ratio, O1, O2 over BE. To remember, for the process, the first thing we need to decide is to pick one point in the figure to balance the entire figure around. How many choices do we have right here? Right. So what is the center now? How many choices? How many viable choices? Which points are the viable choices for the center of mass of this system? Right, we have 2 here, right? Because you can choose either O1 or O2. But which one? Now we have the problem of choosing which one to balance. So do you want to favor one over the other? Right, you want to do both. You don't want to favor one over the other. In fact, you need to use both because this guy, the ratio we're trying to calculate, O1, O2, is not something that's directly in a balancing equation. Well, I mean, you could, but not, particularly not in the original triangles system, okay? So the first thing you do is to choose which point to balance around. Let's say we choose O1. Okay. So for that, what can we do here? Let's say I want to assign the mass at A. What number should I use for the mass at A? For the center of mass at O1. Okay. Right. Okay. Let's use 10 for what? It's 10 for A. Okay. So tell me, why do you want to use 10 for A? Is there any number where you think it's going to make your calculations easier down the road? Because if you want to balance A and C around E, the ratio of AE over CE is 2 over 3. Right? It's not very good if you use the 10, because it's not a multiple of either, not a multiple of 3. That's the problem. So, right. Somebody said it's 3. I don't want to use big numbers. I prefer the smallest possible. That makes the mass of C integer. Okay, so with that, we immediately know the mass of what? So with the we assigned 3 to mass 3 to A. What other masses do we immediately know? Well, for instance, what's the mass of C here? Right, C is 2, because 2 times 3 is equal to 3 times 2. And B, what's the mass at B? Can somebody tell me what's the mass of B? Okay, 2. Okay. So do I get other answers? So is there another answer for the mass at B? Okay, so how do you get 3? Hey, Jojo Canada, how did you get 3? Okay, so okay, let me ask you. So can you balance around G? Jojo Canada said if you balance around G, you get 3 for B. But can you balance around G? So why not? So why can you not balance around G? Okay, so that's the answer one by one. So first, we're trying to get at, remember, what's the center of mass we're trying to make it to be? Which point are we're balancing around O1. What are the Cevians or transversals passing through O1? Okay, so can someone please tell me what Cevians, right? BE and CF. Let me highlight them so you can see. Only these two, okay? Only these two pass through O1, which means you can only balance around what? If you want to make O1 the center of mass, you can only balance it around which points? Yes, you can only balance around the feet of these two Sibians, E and F, because these guys, D and G, they are not in the system. They are not intermediate center of masses. Okay, centers of masses, right? Because we're not making O2 the center mass of the system. So you can only make balance around E and F. So we already did with E. With F, then the mass at B would be, I'm sorry, would be 3 times 2 AF. So MA times AF over FB, which is 4. So it's 3 over 2, right? So after this, what do we get? So after this, what can I get? What information can I derive out of it? That's connected to the answer we're trying to calculate. Don't forget what you need to do when you're trying to get to. Okay, don't forget your target. Yeah, I mean you can have the mass of F, but with the mass of B and the mass of E, what's the mass of E here? Can somebody tell me the mass of E? E is 5, just mass of A plus mass of C. So with the mass of E and B known, what do I know? What do I know that's connected to the quantity we're trying to calculate? Right. So, well, I mean, I would use BO1. For this, I immediately know BO1 over EO1 is equal to ME, the inverse ratio of the masses, over MB. ME is just 5, MB is just 3 over 2, so it's 10 over 3. Okay. And with this, because we're trying to get something over BE, I want to use the technique of this will immediately give you BOE over BO1. I'm sorry, I got some Chinese in there. Did anybody notice? Plus EO1 is equal to 10 over 13. So which means BO1 over BE is 10 over 13. Okay. Oh, I would highly recommend that you start learning it. It's a very nice language. And, there's 1.5 billion people speaking it. There must be something right about it. I'm sorry, I'm just joking. Okay. So now after this, what do we do? Okay. Regrettably, we haven't implemented a translator in the chat window. Okay. Maybe that's one of our next features. Okay. In any case, so what do we do next? Right. We want to balance around O2, right? Because that's the thing that's connected to the expression we're trying to compute. Let me try to draw a new diagram. Okay, in your real exercises or tests, you should do the same thing. Always use a brand new figure for a different center of mass. Okay, so let me try to draw it. I won't care much about the proportions, but so it's A, B, C. So AF, and then this guy is this midpoint. In fact, I don't even need to draw CF. This time I won't draw it because it actually confused some people in deciding which point to balance around. So this time I won't draw the unrelated Sivian CF. So G is here, okay, and the E, B, and DG intersect at O2. Okay, so we know this is 2, this is 3, this is 2, this is 2, and this one is 3, 1, 2. Sorry for the proportional segments. So what do we do here? It's a scenario of what? What do we need to do? We simply need the mass around B, right? Why? Because the Sivian BE intersects with a transversal DG. Okay? Okay. So how do we want to assign the masses? Let me mark this guy somewhere. So let's always start with A, right? Why not? So right, good, thank you. So I'll make it 3. Then immediately I know the mass for C is 2, right? Balancing around E. And then I immediately know the mass of B is also 2. But on which side, right? Which side of the mass at B is 2? Right, on the BC side, on the upper side. What about the other side? What about on the AB side of mass at B? So it's MA times AG is equal to, let me call it MBD for the downward one, okay? Times BG, the balancing equation, just so those people who haven't seen this before, okay? So this one MA is just 3, AG is 3, MBD is the one we're trying to solve, and then BG is 3, right? So the left side is 3. Now after this, what do we do? Right, we need the mass at B is just the left and right side added together is 5. Then what do we do next? Wait, is this correct? Did we make something? Did we do something wrong? Right. So the mass at E is just sum of the masses at A and C is 5. So after this, we would know BO2 over EO2 is equal to ME over MB, the inverse ratio of the masses, which is just 5 over 5 is 1. Okay, but I need this guy over the entire thing. It's just 1/2. So remember, we got this, and we got this. So we take the difference, we'll go back. 0102 It's just BO1 minus BO2, okay? BO1 minus BO2, okay? So this, then we got O1, O2 over B is just 10 over 13 minus 1 half, 26 over 19, okay? So again, the two things, okay, to note here. One, because now there are more than one choices for center of mass O1 and O2, so you need to do them one at a time, okay? And when you do each one, you only want to use the intermediate points associated with that center of mass, okay? Like for O2, let me jump here. For O2 at the center of mass, the only intermediate ones are D, G, points you can balance around and E, not F. Okay? So that's the most important thing to remember in dealing with a more complex system like this. Okay? All right? I think we have covered enough examples. In fact, all the common patterns that MPG can be applied to. So let's do some theoretical work. I understand that it's already past the stopping time for this lesson, but I really want to cover a little bit of the theoretical foundation. The reason being that, well, if nothing else, it was done by myself, okay? Because the reason being that there was some, highly heated debate in WeChat groups about the legitimacy of mass point geometry as a method in proving or even computing ratios and line segment length. Someone who actually got an IMO silver medal basically kept discrediting this method. Because I tried to teach this method to my own kids. I really want to feel secure myself also, right? So I want to find out whether there is a solid foundation or that there is in fact a theorem behind it. So that's why I dive into discovering basically these two theorems, okay? I mean, not really discovering, formulating, okay? I try to formulate the two theorems to basically make the mass point geometry method quote quote sound, at least to some people, okay? So the first theorem really deals with the two cevians intersecting inside the triangle. It says they're inside the triangle ABC. And there are two cevians, BD and CE, intersecting at G. I picked G for gravity, okay? And then the theorem says for any positive real numbers M, A, B, C satisfying this ratio, MA over MB is equal to BE over AE. Wait, did I calculate something wrong? Oh, yeah. Sorry. You're right. Okay. It's 7. It's 20 minus 13. Sorry about it. Thank you for pointing out. Okay. Yeah. So, and then MA over MC is equal to CD over AD. Then it says the ratio between CG and BG is this. And then BG over DG is this. Okay. Now, please note that I didn't say anything about masses. I wanted to make it a pure mathematical formulation. Okay. Well, of course, I mean, after the proof, I will explain how it's tied to basically what we just went through, or to physics. But at this moment, I don't want to say anything about masses or center of mass. Nothing. It's pure numbers and ratios. Okay, I want to build a pure mathematical foundation. Okay, so to do that, because we're running short on time, I will be fast on the proofs. So the way to do this, I'll use Menelaus. Okay, the way to do it. So for those people who are watching who don't know the English name but may know the Chinese name, I'll write the Chinese. Mei. Mei Nie. Is it 老师? I don't know how to write this 聂. Okay. So 梅涅老师定理. Okay. So Menelaus theorem. Okay. So the way to do it, I do it. Wait, CG over EG, B, AB. So the way I did it was to apply Menelaus on triangle ACE with the transversal DG. DGB, okay? So basically, the transversal, this DG cuts all three sides, right, of the triangle ACE. Okay? So let me highlight extend it. So the way to apply Menelaus, it says, let me start with C. You walk around the triangle ACE. I'll start with C. And then vertex 2, intermediate, CG, intermediate to vertex over EG times vertex 2, intermediate. Now it's extended, but it's still intermediate, BE, and then intermediate to vertex AB, okay, times vertex to intermediate AD, and then intermediate to vertex over CD. Now this is equal to what? So what I'm using right now, what I'm stating, this equality is exactly what Menelaus says. Okay, so I won't go into detail. We won't have time for that. But what I'm saying, basically, you have a triangle ACE, and your transversal DGB cuts all three sides. Okay, at DGB, and then you walk around the triangle with ratios like this multiplied together. It has to be equal to 1. That's what Menelaus says. Okay. I'm trying to teach you guys how to remember Menelaus. Okay. So you walk around the triangle in the fixed direction. You don't walk backwards. Okay. If you walk forward, you walk only forward. If you walk backward, you walk only backward. You either counterclockwise or clockwise, but not, you don't want to change the direction in the middle. So from C vertex to intermediate, CG, over intermediate to vertex to GE, and then vertex to intermediate, BE, over intermediate to vertex, BA or AB, same thing here, and then vertex to intermediate AD, over intermediate to vertex. Okay, so this one. This product needs to be equal to 1. Okay, and then you plug in, right? So we know BE over AE is MA over MB by this condition. Okay, so this will give me the middle ratio in the product of this MA over MA plus MB. Okay, and then I already know CD over AD, right? Because it's this guy. So this together will give me, you plug in these two ratios into this equation, you will get CG over EG is equal to MA plus MB. I won't go to show the steps, but that's mechanical, okay? Over MC. And with exactly the same technique, the same reasoning, you got the other one. You got this one. So similarly, you have BG over DG is equal to MA plus MC over MB. Let me try to shrink it so you can see the whole thing. Again, I want to remind everyone, up until this point, I did not say anything about masses or weight or center of mass, okay? All I did is pure mathematical algebraic manipulations with the conditions, okay? Now, what does the theorem say? Essentially, it says if you can assign, let's say if you assign the mass MA to point A, okay, and then MB in such a way that it balances around E because of this ratio, and also make the masses at C satisfying this ratio, balancing around D, then CG over EG, this guy, is this ratio. So remember, that's exactly what we did. We first, in the examples, right? We first determine MA, we use the ratio of AD over CD to get MC, which will satisfy this. And we also use the ratio AE over BE to get the mass at B, satisfying this ratio. And then we say the mass of E is just MA plus MB. And then you immediately know that the ratio has to be this. I mean, this ratio according to the MPG method. But with the math proof, it is indeed this. I mean, this ratio. Basically, the inverse ratio of these two masses at E and C. Okay? So, I want to, basically, that's the proof. And how it's tied up to the MPG method. I want to ask everybody, what's the degree of freedom? Let's say the diagram, is fixed. A, B, C, D, and E fixed. What's the degree of freedom in assigning the masses MA, MB, and MC? If I have, right, so the ratios, you're right. So how many ratio conditions do I have? Or how many constraints do I have? Okay, you're right. Yeah. So, but I'm trying to ask you guys, what's the degree of freedom here? If I have the triangle ABC fixed, then D and E fixed, what's the degree of freedom in assigning the masses MA, MB, MC, satisfying these two? I have only two conditions. I have two conditions. How many variables? I have three. Okay? So that's why you can arbitrarily pick your first weight. Because I have two conditions, but I have three variables to assign. Okay? In order to satisfy the ratio, that's why the first weight can be arbitrarily chosen to make your calculations more convenient. Okay? And let me see. And so the physics interpretation is the same thing, right? If I have masses at A, B, C, to calculate its center of mass, either I first calculate the center of mass of the subsystem A and B, to arrive at E, and then use E and C to calculate the center of mass at G. Okay? So when does this end? I want to try to finish the second theorem, and then maybe I'll stop there, okay? But you guys, you can feel free to leave. I will post this as a video in the lesson, so you can watch it anytime you want. Okay, so for those people who can stay, maybe I'll try to quickly go through the second theorem. Okay. So the second theorem says, basically, it's the transversal case. Okay, you have a triangle ABC. Just a second. Let me try to draw it so it won't go out of the page. So you have ABC, and then you have a transversal EF, And then you have the Cevian AD intersecting again at the point G. Okay. And then it says for any positive real numbers, MA1, MA2, remember the, I won't mention the word here because I want to make it pure math. Okay. That's why we have two of them at A. Okay. So MB, sorry for the misformatting. Okay. And MC, satisfying these ratios, then you're asked to prove these two ratios. Okay, so for this, I will go through very quickly. To do that, I want to use again Menelaus. That's why the title of this lesson is MPG is Menelaus. Okay, so I extend EF to intersect with BC's extension at P. Okay, and the first, I will use Menelaus with the triangle ABC. I want to I want to write Chinese because that's more indicative. Okay, because I want to write that English word too long. Okay, so with Menelaus, you got on triangle ABC. Sorry, let me. ABC with EFP as transversal. Okay. The reason why I'm writing this out in so much detail is to also help you remember Menelaus, because in most explanations or solutions, they just say, "Oh, use Menelaus," but I mean, very few people can remember how to use it or even the exact format, because they are tied with the specific notations instead of the ideas. I'm trying to tell you the ideas behind the Menelaus. Okay, the idea is very simple: a triangle with a transversal, and then you walk around the triangle in a fixed order, vertex to intermediate points, intermediate to vertical points, the ratio, and then multiply together equal to 1. Okay, so with this, I start from P. Okay, from P to C, intermediate. Wait, did I do it wrong? PC over PB. Right, sorry. Right. I start with C. C to intermediate is P on the side BC. Okay, so it's PC, and then intermediate to vertex PB times vertex to intermediate BE over intermediate to vertex AE. And then vertex A to intermediate F, AF over CF. Okay, and then intermediate to vertex again is equal to 1. That's what Menelaus says. Okay, and then from this, we plug in the given ratios. It gives us PC over PB in the known numbers. So it's MB over MA1 times MA2 over MC. Okay, and from here you will get you do the sum of the numerator and denominator again. You get PC over BC is equal to MA2 over MB times MB over MA1 times MC minus MA2 MB. Okay, so that's oh, it's not the sum, it's a difference, because BC is PB minus PC. Okay, and then we use the fact that the BD CD over BD is this solution. I mean, this condition is just MB over MC. So this will give me CD over BC equal to MB over MB plus MC. Okay, so these two together give me the ratio of PC over CD. Okay, and D is missing here. See, with CD is it's kind of messy, but it's just mechanical algebraic manipulation. Okay, over MA1 MC minus MA2 MB, and from here you get PC over PD is equal to MA2 times MB plus MC over MA1 plus MA2 times MC. Okay, and then you use 2 more Menelaus. It's this one. Now, because I calculated PC over PD, the reason why I did that is I want to use Menelaus on this triangle, ACD, with this PFG as a transversal. Okay, and then there are 2 more Menelaus applications because of time constraints, and also it's kind of very involving algebraically. I think I should just stop here. Maybe I will post my handwritten solution to the class. So for those people who are interested in knowing the complete proof, please refer to the post. Also, I want to jump to the real context examples, because nowadays most everyone either heard of or tried or know about the basic applications of mass point geometry. So in the real context problems, it's no longer like 10 or 20 years ago, when they are just straightforward applications of MPG. So for this one is 2019 AMC8 problem 24. It's about area, but it's still a very straightforward application of MPG for this one. It's just the first case. It's just the concurrent Sevians application. Okay, right. Does this look familiar to you? I don't know whether you got it in your real test. Right, you're right. Yeah, but you're right. I mean, on AF pages, there are more examples, but I don't think you can find anywhere. In fact, I mean, we tried to look for it when we were engaged in basically debating about the validity of the MPG in rigorously solving math problems. I mean, I searched on the internet. I couldn't find any, published rigorous proofs of the method. So these two theorems are basically my attempt in establishing at least to my own satisfaction the mathematical rigor of the math point geometry method. Okay, so you're right. I mean, you can go on AOPS to find more examples. The second example I was going to cover is I think this is wrong. This is the 10A problem 19. It's also a very straightforward applications of MPG with concurrent Sevians in this triangle. Okay. Of course, you need some trivial, similarity ratios like, BP over DP is BE over AD is 1/3, and BQ over DQ is 2/3. But those are the parallel ratios. Those are trivial to to arrive. Other than those two trivial ratios, one application of MPG solved this problem. Okay. Okay. All right. Which problem you want me to go back to? This one? Oh, so you didn't know math points. Okay, that's fine. Yeah. So what's the question? Okay, that's all right. Yeah. So this is very straightforward applications, right? Because I mean they're just two intersecting Sevians. Okay, I think my presentation of the MPG is down here, and I will post my handwritten proofs for those two theorems to the class. You can, read it at your leisure. But I want to particularly remind you guys, and particularly your parents, that I'm going to publish the 4 classes for the introductory algebra and geometry, as well as the AMC 1012 and the AME summer camp classes. So you are welcome to enroll in the classes. If you have any questions, feel free to post in any questions in the class, or have your parents post their questions in the WeChat groups. I want to show you how to send messages to each other, or how I will communicate with you. So let me just terminate the broadcast, the live broadcast. I will, and again, thank you very much. Thank you very much for your attention and for your interest. I will terminate the live broadcast, and maybe I shouldn't. I will show you the screen. Okay, I won't terminate live broadcast. I want to show you how to interact. Okay, so both between you and me and amongst yourselves. Okay, so I go back to the app, the DDAR learning app. Okay, and sorry, it wouldn't. Wait, I can. Okay, I can do it. So I will rotate it to this mode, and wait, I still I'm trying to let you know that, I mean, tell you how you can communicate with me even without using the discussion area. Right now, you can use the discussion area to chat with me, right? But you don't need to even after this class is over. There is, um, I don't know how I can toggle it. If I go back, I click the left arrow at the upper left corner, then I'll terminate the video stream. Okay, let me try to just do this. Let me send you a message. Uh, so from the course page, you go to my courses. Then you click whatever course. For this one, it's demo math point geometry is Menelaus. You click it, and then there's a join class group to learn more. Okay, and then that goes to the so-called class page. Okay, and then you click the discussion. There you can post any messages to anyone. I mean, you post a message to the group, everybody in the group will see, including myself, and I will be using that to post the handwritten proof for those two theorems. I will also, put those two context examples as homework if you are in the mood to do it, okay, to the class. That's also accessible through that class group. With that, again, I want to thank everybody for coming, and I hope I will see at least some of you in some of my classes. Okay, all right. Thank you very much. Have a good rest of the night, and good night. Bye bye.